This is the second video of Chapter 7. This one is on the planet Saturn. To get to Saturn requires what is called gravitational slingshotting. The Cassini orbiter, which was sent to Saturn recently, was propelled actually towards Venus in order to steal some of Venus's momentum as it's going around the sun, and hence pick up a greater speed from taking that momentum from the planet. So actually, rather than shooting at Saturn, we actually shoot at Venus, pick up some momentum, maybe it comes back to Earth, picks up some of Earth's momentum, goes back to Venus, picks up momentum, and then is projected out towards the outer solar system, towards Jupiter, get a gravity boost from that, and then go to Saturn. So that's exactly what the Cassini did. And we can see it did a flyby by Venus in 1998, another flyby in 1999, went by Earth in 1999, each time picking up more speed, free energy. So you don't have to have all this rocket energy. There's no way we could have a rocket that big to get this much energy. Hence, it can go to the outer solar system much faster, get there in a few years rather than many years. It went by Jupiter, picked up a last bit of gravitational slingshotting there, and finally arrived at Saturn. A lot of what we know about Saturn now is from the recent mission of Cassini to Saturn. Saturn is the most distant planet known to ancient astronomers. It's much further than Jupiter, and it's clearly seen by the naked eye, and of course regarded as the most beautiful sight in our solar system. Named for the Roman god of agriculture, actually the father of Zeus, Kronos, is also called in the Roman world Saturn. Kronos was the one who swallowed all of his children, so that because he had been prophesied that one of his children would revolt and dethrone him, and his wife Rhea made him eat a stone instead of Zeus, so that he wouldn't eat all of his children, and eventually Zeus was the one who overthrew him. Saturn is the only planet that is less dense than water. So if Saturn were a huge beach ball, it actually would float on water. It's the only planet that would do so, less dense than water. It's a gaseous fluid object. It has no solid surface. It does have a rocky core, but basically before you get there, it would be purely gas and ice layers before you got to that rocky core. Saturn's gravity is 2.5 times less than Jupiter, so it's actually more on the order of similar to our gravity. It's only 40% that of Jupiter, and Saturn has, at least in this accounting, 31 moons. Some accountings have as many as 48 moons currently for Saturn. In this picture, you can see 4 of them near the equator of the planet. Here's a beautiful picture. Radius of Saturn is 9.5 times the radius of the Earth. The mass of Saturn is 95 times greater than the mass of Earth. Saturn's distance from the Sun is 9.5 astronomical units, so it's 9.5 times greater than our distance from the Sun. And Saturn revolves around the Sun in 29.5 Earth years. So these are all easy numbers to remember. Radius is 9.5 times, mass is 95 times, distance is 9.5 astronomical units, time around the Sun is 29.5 Earth years. If we were to rate Saturn on a scale of 1 to 10, it probably would come out as a 9.5. Saturn undergoes rapid differential rotation, which means the differential means that not all parts of its atmosphere are rotating at the same rate. It requires 9.5 hours to complete one rotation. Now, actually, it's 10.5 hours, so that didn't quite fit into that 9.5 zone, but it's pretty close. The rotation axis is tilted 27 degrees from its orbital plane, and that's a similar tilt to Earth, Mars, and Neptune. So we have 4 planets that are within about 3 degrees of tilt of each other. Another nice picture of Saturn. Saturn's equatorial flow reaches 1,500 kilometers per hour. That's much more than hurricane strength. That is maybe 10 times hurricane strength. About 950 miles per hour, so that's easy to remember. Winds of 950 miles per hour, so that is more than 10 times hurricane strength if a hurricane is 74 miles per hour officially. So those would be winds that we have not any idea how bad that would be. Saturn has cloud bands like Jupiter, but less colorful. Here's a recent picture, though, that looks pretty good. The cloud level is 3 times thicker due to less gravity, and the cloud thickness doesn't allow the lower belts to be seen. So it's a little bit more uniform in color than Jupiter, but in this picture you can see some distinction of the bands, and also what is called a dragon storm over here. Interesting storm here in this band over here. Saturn's atmosphere is composed mostly of hydrogen, 92.4%, and helium, 7.4%, with traces of ammonia, methane, and water vapor. The helium amount is lower than, say, Jupiter's because it's believed that the helium is condensing and raining coreward towards the planet, the rest of the planet. So helium is the rain on Saturn. The temperature of the cloud tops is 95 degrees Kelvin, or about minus 285 degrees Fahrenheit. Here's a look at Saturn's atmosphere. You have a stratosphere, troposphere, ammonia ice layer, ammonium hydrosulfide ice, just like on Jupiter, but you don't see these brown bands as prevalent, and probably water ice below that. Helium is absent in the outer atmosphere because it condenses and rains inward toward the core. This allows Saturn's atmosphere to heat up, and Saturn emits more heat due to this condensation of the helium gas. This is to what Earth experiences in its water condensation. So near the Earth's equator, as heat is hitting the equator, water evaporates and then condenses and it releases more heat, helps to fuel the structure of storms like hurricanes, and the same sort of thing is happening on Saturn. Here's a nice picture using false color, revealing with more detail the belts, bands, and spotty storms that are similar to Jupiter. Here's a closer look. Some spotty storms and fan-like structure. Very, very beautiful picture. Here's Saturn. And if we were able to look inside Saturn, what would we see? Let's take a look. So we looked into the interior of Saturn. We would find an atmosphere on the surface, and then sort of a mantle of fluid metallic molecular hydrogen. And then as we get closer to the core, metallic hydrogen. Hydrogen in its metallic form, because hydrogen is a metal. And so in this sort of outer core, this metallic material is swirling around, helping to develop the magnetic field of Saturn. And possibly inside that, a rocky core, which is larger than the size of Earth, maybe 15 times the mass of Earth in that rocky core. Saturn emits 3 times as much energy as it receives from the Sun, so it's actually emitting energy, and this is believed to come from the helium rain condensing, releasing the energy, and this energy being emitted. This is more energy than any other planet, or more of a factor of energy than any other planet, to release 3 times as much as you receive. Here's a look at Saturn's magnetic field as compared to the Earth. The Earth, as we know, spins pretty rapidly in 24 hours, and because of its spin and its interior material of iron and metals, creates a significant enough magnetic field, and this kind of result of spinning this material and creating a magnetic field is called the dynamo effect. And like Jupiter and the Earth, Saturn is also a good example of the dynamo effect, the dynamo theory, which means that with the spin, you have the spin axis, the magnetic poles are actually aligned pretty close to the rotation or spin axis. For Saturn, this magnetic field is caused by the spinning metallic hydrogen. Its field is only 1/20th as strong as Jupiter's, so maybe it doesn't have as much metallic hydrogen. However, that is still 1,000 times stronger than the Earth's magnetic field, so it's still a very significant and large magnetic field. And with any magnetic field, you would have the effect, as it comes near the poles, of auroras. So Saturn traps charged particles near its poles, and we have auroral displays at the poles, and here's some very nice pictures showing these auroras near the geographic poles of Saturn. Here's a picture taken by the Chandra X-ray telescope. And it's showing that Saturn is actually emitting X-rays about its equator. This picture taken in 2004. This is unlike Jupiter, which emits X-rays at its poles, and the reason for this is still unknown. So there's no reason to know. I mean, it's probably due somehow to the way that the metallic hydrogen is spinning, but it's still not known why there's a difference between Saturn and Jupiter, and why it's emitting these X-rays at all. Here's another recent discovery of Saturn. Saturn has 2 large storms at each respective pole. Huge storms at each respective pole. Here's the North Pole storm and the South Pole storm. And the North Pole storm even has some hexagonal appearance to it. very unusual in nature to have such a beautiful structure somewhat randomly, or maybe not randomly. It has probably something to do with the inner makings of Saturn. Well, we have this hexagonal structure at the North Pole and another round storm at the South Pole, both large storms at the poles. Here's a look at that North Pole storm. And as you look at this, I want you to really focus in on this storm as we take a look at it as it rotates over time. Really look at it good. Look at the center of this picture really well. You like astronomy, don't you? You do. You like astronomy, don't you? Oh, sorry. Here's a look at Saturn. You can see 4 of its moons here near the equatorial plane, the same plane as the rings. Not sure which moons those are. Here's another great look at Saturn. You can see the ring. We're looking at edge on here. See the ring system? We see some moons right near that equatorial plane. Beautiful picture. And here's Titan over here. And you can see the shadow of Titan down here on the planet Saturn. So what a great picture. Most of Saturn's moons are found near that equatorial plane along with the rings. And all but one of the moons orbit prograde with the planet. So the planet is going prograde around the Sun, counterclockwise. Planet is spinning prograde, and the moons are spinning prograde, revolving prograde around Saturn itself. So this suggests an origin with the planet, that these moons are actually having residual effects of the same effects of the solar system itself, all this prograde motion, except for one satellite around Saturn. Here's another great picture, and we can see actually Titan is eclipsing the planet. So we're just lucky enough in this picture that Titan is actually on the image of the planet, and we can see the shadow of Titan again on the planet as well. Here's a picture of the moon Mimas against the ring system, or Saturn's northern hemisphere, but so the shadows on the northern hemisphere are from the ring system. Here's Dione, also against the planet Saturn in the background. It's a great picture. Here's Phoebe. Phoebe is Saturn's only moon to orbit retrograde. As you look at Phoebe, it kind of looks like an asteroid. So it probably was a captured asteroid. So most of the moons are going prograde. The one moon that's going in the opposite direction probably was captured after the formation, sometime later, as a captured asteroid. Here's Iapetus. Iapetus turns as it revolves, so it's gravitationally fixed to Saturn. So it's always showing the same face to Saturn. And in fact, its forward face is dark in color, and its reverse face is light in color. So it's possibly picking up material as it's going through its orbit about Saturn that has darkened the forward face. More on these moons later when we're specifically talking about the Jovian moons. We're just trying to do an overview here. Here's a look at Rhea. As we said, Rhea was the wife of Kronos, or Saturn. And so here's a moon named after Saturn's wife. The second largest moon of Saturn, after Titan. And Kronos was the father of the Titans. Here is Titan. This picture taken by Voyager 2, or Voyager 1. Titan has an atmosphere of nitrogen 90%, argon 10%, and methane, a trace of methane. Our atmosphere on Earth is about 80% nitrogen, but a primordial Earth probably had an atmosphere very similar to Titan's, about 90% nitrogen, traces of these other gases, not any oxygen. That's what a primordial Earth probably was like. This atmosphere is actually denser than our atmosphere. It's about 60% denser, producing the reddish color. And this is the Voyager photo. In other words, the Voyagers were sent out to look at all the Jovian planets, the 2 Voyager spacecraft. And when they got to Saturn, they saw Titan. They said, well, Titan has some Earth-like features. You know, this atmosphere, this thick atmosphere with nitrogen. That's pretty interesting. So, Voyager 1 was sacrificed to look at Titan. So, Voyager 2 went on to look at the other Jovians. Voyager 1 was moved off course to take this picture of Titan, and that's all it got, though. Just this fuzzy picture of Titan. So it was kind of a letdown that it didn't get more from its diversion. Here's a more recent picture of Titan. This one was taken by the Cassini orbiter, which, as we said, finally reached Saturn in 2003 and took this picture of Titan in 2004. The bright region on this picture is called Xanadu. Cassini had a probe called the Huygens probe, named after Christian Huygens, who has gotten credit for discovering, or at least identifying, the rings of Saturn. And so this probe was launched into Titan to try to investigate Titan. And hence, as Cassini got close, it launched this probe into Titan, into this area here. Here's a blow-up of the eventual touchdown area of the Huygens probe. As the probe descended, it started taking pictures of the surface of Titan, and here is a very interesting picture. It kind of looks like a shoreline to a lake, some kind of sea boundary, highlands and lowlands. And indeed probably is a lake, but it's not a lake of water. It is a lake of methane, liquid methane. Here are some inflow channels into this lake. So we have what appears to be rivers and channels and lakes of not water, but liquid fuel, methane or ethane combination on Titan. Because on Titan, the atmosphere rains methane. The Huygens probe finally landed and took this picture, showing a very orange color on the surface of Titan and a rocky surface. There's only a couple pictures taken because the battery on the Huygens probe was not strong enough to transmit for very long, and soon the Cassini orbiter, which was acting as a middleman transmitting to Earth, finally went out of range. So we only got a little bit of information from the surface of Titan. Here's a look at the relative size of these rocks that you're looking at on the surface of Titan. This rock being about 10 centimeters long, about that long right there. More on Titan later when we discuss again the Jovian moons. But here's a very interesting moon of Saturn, Enceladus. Enceladus is an icy moon. The ice comprised of water, and this icy moon reflects 90% of the light. It's the most reflective object in our solar system. Recently, it was discovered that Enceladus has water geysers. So this icy moon probably has liquid water underneath its ice, and that liquid water shoots out into geysers, and this the residue of this geyser activity helps to develop the E ring of Saturn's rings. The E ring of Saturn's rings is water, snow, more or less, from the geysers of Enceladus. Enceladus is right near the E ring of Saturn. Very interesting, because if there's water and liquid water on any other terrestrial object, then we always think that there's a possibility of life, because there must be some kind of internal heat source that's allowing this to be liquid water. And in the case of Enceladus, it's probably the gravitational tidal flexing that's going on as it's being pulled by Saturn and being pulled by the other moons in the outer atmosphere. So this pulling between Saturn and moons are pulling Enceladus back and forth, creating an energy source from its interior. So Enceladus has been in the news lately as one of those worlds, one of those few worlds out there that is very interesting, probably even more interesting than Mars itself, as a possible location of life. Certainly liquid water. Here's Enceladus is relatively small, though. Here's how it compares to the moon, and the moon to the Earth itself. 309 miles in diameter. Here's how it would compare in size to Great Britain. And bring it all home, here's how Enceladus would compare in size to Alabama. It would extend just about from the northern border of Alabama down to the southern border with Florida. That is the size of Enceladus. So it's a relatively small moon. One distinguishing feature on Enceladus is these three grooves, four grooves really, if you look at it, on this bottom side here, and they have been called tiger's stripes. And evidently then there is some tiger out in space here, and he's not very happy, and he's been responsible for swiping and causing these stripes on the surface of Enceladus. No, it's just some kind of ancient scraping on Enceladus, which is as yet unexplained. But the majority of the geysers are coming from those tiger stripe areas, so that's where the ice is opening up and releasing these water jets. To conclude our discussion of Saturn, here's a very interesting recent picture, also taken by Cassini, but it was taken by Cassini when the sun was blocked by Cassini. So it's an eclipse of the sun by the Saturn itself, and by doing so, it kind of backlights the whole perimeter and the whole environment around Saturn. And we can see a few of the moons here, but here's a very interesting dot right here. This dot right here in this picture is the Earth. Now it looks like it's within Saturn's ring system, but that's just a matter of perspective. It's the Earth is hard to see from Saturn because it's so close to the Sun in relation to Saturn. So your best chance to see it is during a Saturn eclipse. And by doing so, we can see the Earth within Saturn's, at least in the perspective of Saturn's ring, right here. If we blow this up, we can see the Earth. That little blue dot there is us. So we need to wave. Maybe we can see ourselves waving in this picture. That concludes our lecture, our second lecture in Chapter 7, this one on Saturn.